Somewhere in northern Japan, a factory controls 80% of the global market for the steel forgings that sit at the heart of nuclear power plants. And the reason they dominate has nothing to do with patents or trade secrets. Japan Steelworks in the city of Muroran produces components so massive and so precise that machines simply cannot make them, which means the work falls to human hands guiding 600-ton masses of glowing steel through presses that apply 140 meganewtons of force. The component is called a reactor pressure vessel. Picture a cylindrical steel container standing 12 meters high with walls up to 25 centimeters thick, weighing somewhere between 320 and 500 tons when complete. These vessels house the reactor core, the coolant, and the control mechanisms, operating at temperatures between 300 and 350 degrees Celsius under pressures reaching 2,000 pounds per square inch. What makes them different from almost everything else in a nuclear plant is that they cannot be replaced. Whatever vessel goes in at the start stays there for 60 to 80 years. That's the design life, and there are no second chances. The metallurgy explains everything. Welds fail. Under decades of neutron bombardment from the reactor core, weld zones become susceptible to embrittlement and cracking in ways that solid steel does not. Japan Steelworks solved this problem by producing reactor components from single massive steel ingots with no welds at all, creating continuous grain flow through the entire piece. What this requires, though, is working with steel on a scale that defies easy comprehension. Muroran operates two 14,000-ton hydraulic presses, the largest in commercial operation anywhere on Earth. The facility includes a 120-ton electric arc furnace, a 150-ton electro-slag remelting furnace for achieving the highest purity, and wharf cranes ranging from 70 tons to 730 tons of capacity. The plant produced a 670-ton steel ingot in 2011, the largest commercial steel ingot ever cast. What stands out is that all of this equipment exists to support a process that still depends on human judgment, workers watching the color of heated metal, and making decisions no algorithm can replicate. Manufacturing starts with the ingot. Steel melts in electric arc furnaces, then passes through vacuum degassing to remove hydrogen. It then undergoes electroslag remelting, where argon gas eliminates impurities, while manganese, chromium, and nickel are added for hardness. This phase alone takes 2 to 4 weeks. The ingot then heats slowly to avoid thermal shock cracking, reaching temperatures between 1200 and 1290 degrees Celsius, at rates of roughly 20 to 30 degrees per hour, with soak times of 45 minutes to an hour per inch of thickness. Heating a single ingot can take 24 to 72 hours per cycle, and that is before any forging begins. The forging sequence includes cogging to break down cast structure, upsetting to reduce height while increasing diameter, drawing out to lengthen the piece, and ring rolling to form hollow rings. A single major component may require 2 to 4 months of repeated heating and pressing cycles, and this is where automation fails completely. Open die forging requires continuous repositioning of the workpiece between press strokes, real-time adjustment of direction and angle, and constant decisions about where to apply the next deformation. Industry sources describe it plainly. The workpiece must be constantly moved as it is worked. At this scale, with pieces weighing hundreds of tons, only skilled human operators can manage it. What most people miss is that each ingot behaves differently, each one unique. Segregation patterns, the way different elements distribute themselves during solidification, vary with every casting. Research shows that deformation in these materials is not uniform because of the large size of the forgings, resulting in different grain sizes in different areas of the same piece. Experienced forgers rely on judgment, reading temperature by metal color. Cherry red indicates around 700 degrees Celsius, and white indicates 1,300 degrees Celsius. They watch for surface cracking that signals the metal has cooled too much, look for laps and folds from improper flow, and monitor how the steel resists pressure. Too hot, and the metal suffers grain growth and potential burning. Too cold, and it cracks. The window between those failures is narrow, and it shifts based on conditions inside each individual ingot that cannot be fully predicted. That's why this work still belongs to humans. Japan Steel Works traces its founding to November 1st, 1907, as a joint venture between Japanese and British firms. During World War II, the Muroran plant forged the 18-inch cannons for the battleship Yamato, the largest caliber naval artillery ever deployed. On July 15, 1945, 200 workers died at the facility during Allied naval bombardment. The company dissolved under post-war policies on December 11, 1950, and reconstituted itself the same day. Nuclear manufacturing started in 1974, when the company began producing components to United States Nuclear Regulatory Commission standards. What surprised me while researching this was a detail that seems almost too symbolic. Since 1917, the company has maintained a samurai sword-making tradition. A single craftsman still works in a small shack on a hill above the Muroran factory, hammering steel into broadswords using traditional methods. Each sword comes from a 1-kilogram lump of Tamahagane steel, takes months to complete, and sells for approximately 1 million yen. The company's president explained the connection, saying that samurai swords contain the essence of steelmaking technology. Both disciplines require understanding how steel behaves under heat and pressure in ways that cannot be reduced to formulas alone. The mid-2000s brought the nuclear renaissance, a surge in planned reactor construction that pushed demand beyond supply. By 2008, plans existed for 31 new reactors in the United States and 25 in China, and Japan Steel Works could only produce 4 complete reactor sets per year. Generation 3 plus designs made the problem worse, because they require approximately 4,000 tons of steel forgings per reactor, double the requirements of earlier designs, using ingots of 500 to 600 tons instead of 300 to 350. Wait times stretched past 4 years. Utilities paid deposits worth hundreds of millions of dollars before they had even received regulatory approval. The company's general manager of forgings and castings exports described the situation with unusual candor. He said business was too good and at the same time too bad. He said they could not respond to 100% of their customers' requests, and that everyone was mad at them. Japan Steel Works responded with massive investment, completing a 50 billion yen expansion by early 2010 that added a second 14,000-ton press, followed by another 30 billion yen phase in 2011. 80 billion yen total, roughly $837 million. The result was capacity tripling from 4 to 12 reactor sets per year. And then, everything changed. March 11th, 2011 brought the Fukushima Daiichi accident. Here is the detail that changes how the entire story looks. The reactor vessels at Fukushima, vessels Japan Steel Works made in 1967, largely held despite catastrophic cooling failures. 6-inch thick steel containment became an inadvertent test of the company's craftsmanship under extreme conditions. None of that mattered for the market. Global demand for new reactors collapsed, leaving Japan Steel Works with a massive expansion and expectations of only 70% capacity utilization. The following decade saw competition rise. Doosan in South Korea commissioned a 17,000-ton press in 2010. Chinese manufacturers invested billions in new facilities. Global capacity grew from approximately 15 reactor pressure vessels per year in 2008 to approximately 42 by 2021. And Japan Steel Works faced pressure it had not experienced before. Trouble arrived again in 2022, when an internal whistleblower reported quality concerns at the manufacturing subsidiary. Investigation revealed modification and falsification of chemical analysis results, falsification of stress and hardness measurements, and 20 nuclear components affected, with the oldest dating from 2013. 6 cases involved orders for the French utility EDF. The company established a quality management office, implemented reforms, and underwent multinational regulatory inspection. It worked. Briefly, the current picture shows recovery. November 2024 brought a 10 billion yen investment announcement, roughly $70 to $80 million, to expand capacity at Muroran by the end of fiscal year 2028. The company received its first order for small modular reactor parts destined for North America, proving that even new reactor designs require precision forging that only facilities like Muroran can deliver. Driving this recovery is a shift in global energy policy, as decarbonization targets renew interest in nuclear power. France plans 6 new EPR2 units. Canada pursues small modular reactor construction, and the United States extends lifetimes of existing reactors while exploring new designs. Japan Steelworks revised its outlook upward, reporting clear recovery in nuclear business. The reason this matters is that manual forging persists here, not because of technological backwardness, but because the process resists automation at a fundamental level. Each 670-ton ingot is unique. Its internal structure and response to pressure depend on conditions that vary in ways that cannot be fully predicted. Workers who guide these massive pieces through months of heating and reshaping carry knowledge accumulated over generations, knowledge that exists in trained observation and experienced judgment rather than any database. One industry observer described what happens at Mirror in this way. What they do is an art more than a science, and that's why they are the critical path. A single factory in northern Japan, operating equipment that takes years to build and decades to master, remains essential to the global nuclear industry. The vessels it produces will contain radioactive material for 60 years or more, under conditions that would destroy lesser steel. They must be perfect from the start, because they cannot be replaced, and they are still made by hand. If you found this look at industrial manufacturing interesting, please consider subscribing. You will see more stories about the systems and processes that shape our world.